Well, it's a pleasure to introduce Maxim Kontsevich, who will tell us about new axioms for quantum field theory.
Okay, thank you very much. And now I start to share my screen. And a second. Does it work? No. Oops. Disaster. Just a second. I have to. Okay. Okay. A second. Share screen.
That looks good.
Okay, just now you see the white page, suppose, yeah? Yeah.
Yes.
Okay. Okay. Now I go to the first page, which I draw in advance. It's will be very dense picture. It's a kind of Rosetta Stone of axiomatics of quantum field theory. So there are about 5 different axiom systems.
Maxim, you're muted and we can't hear you.
Mute, okay. Are you hear me? Do you hear me?
Yes,
yes, we do.
Okay, good. I don't know why I was muted. Yeah. Okay, so here's this Rosetta Stone of axiomatics of various axiomatics of quantum field theory. There are different languages, and some of them speak to each other, but not all of them speak at the same time. So I start with most classical picture, which is the left upper corner. So we have in quantum field theory, it's in flat Minkowski space-time. You get Hilbert space, action of Poincare group. So the representations are particles, and representations are with all non-negative energy. And then the first axiomatic was by Arthur Whiteman. He said that if you get some kind of like scalar field, it means that at each point you get operator in your Hilbert space, but it will be distribution with values in operators in Hilbert space. And you have unique vacuum vectors, and you can compose several operators different points, consider vacuum expectation value, and you get certain function distribution on nth power of a Minkowski space, which depends on the order, how you order. It's not symmetric things, it depends on the order. But if two xi plus 1 are separated in space-like fashion, then you can permute these two things to the partially symmetric. And there is a big system of axiomatics about the story. Yeah, then one can go 2 ways. Maybe I can go, there was famous weak rotation. People identified with some kind of axiomatics in Euclidean space-time, Sterwalder-Schroeder axiom, which are, in a sense, made up to fit with white maxims by weak rotation. And so you get this expectation values, and they have analytic continuation. It follows from all various properties. And what you get functions depending on n points in Euclidean space. And now it will be completely symmetric, but points should be all pairwise distinct. And the meaning of phi(x) will be not an operator, but a functional on the space of classical configuration. And the kind of meaning, informal meaning of this correlation function in Euclidean setting is you take like Feynman measure, whatever you don't know what is it, and consider correlators of several observables. So you get things which is completely symmetric, and it satisfies another axiom. It's called reflection positivity. If you put several observables in the upper half space and lower half space in symmetric space and in symmetric fashion and make correlator, you get some positive definite scalar product, which eventually gives you a way to reconstruct a Hilbert space. Also, we can go in this direction. Or we can go on us. I think it's also a very ancient story, Haag-Kastler axiomatics. Namely, if you have some domain in your Minkowski space-time, you consider this operator associated to points in the space-time that generates some algebra, and this will be star algebra. And if to enter some axiomatics about this collection of star algebra associated with open domains. If two domains are space-like separated, then this algebra commute with each other. And then much later, there was a way to translate it to put it in kind of curved space-time by Friedenhagen and his collaborators, Brunetti, Werch, and Fuster. So you consider not necessarily flat Lorentzian space-time, and for sufficiently nice space-like hypersurface, you get a Hilbert space. So it will be a priori not one Hilbert space for the whole universe, but depending on what space-time you choose. And if your space-time is globally hyperbolic, has kind of in boundary, out boundary, and there is some vector field which is connect past in the future, which always like light-like, then this Hilbert space associated to one guy, another will be identified. And if you put again some domain in between in the sandwich and put some operators in the thing, you get certain operators which map from one space to another, but it will be exactly the same space. So you get more or less some version of Hack-Kastler axiomatics. And then there is a thing which kind of, there's really no name on this. It's nobody axiomatics. It appeared in 80s, and in topological field theory, it's kind of IT axioms, but I will not speak about topological theories at all. So kind of the most relevant version is two-dimensional conformal field theory axiomatics, which was invented by Graeme Segal, and in fact by Young me in '96 at the same time. And when Graeme visited Moscow, we realized we have the same axioms. Yeah, so what is this axiomatic? If you consider some category metrized Borgisms, so you get certain manifolds with boundary, some and boundary which is kind of co-oriented. There are in and out parts, and then you get tensor functor to vector spaces, which are not Hilbert spaces of general. And this it's kind of a bit similar to this Friedenhagen axiomatics, because you have something like manifold with boundary. You get this when you get the sandwich, you get global hyperbolic space with two space-like boundary and some domain inside. You get three boundary components, and it's a bit similar to this Borgism axiomatics. And Borgism axiomatics is an Euclidean framework, so it's kind of start to talk to Westerwelle-Schrader axiomatics. So you get kind of circle of 5 different axiomatic series, but only 2 attached next to each other talk to each other, and none, they don't talk simultaneously. Yeah, so I divide this picture in 4 pieces because they have flat space-time, or curved space-time, Lorentzian and Euclidean. And the axioms which we propose with Graeme is some modification of this nobody axiomatics, which started to talk to all these axioms, to all these other systems at the same time. So one can, and it's kind of pretty neat. The story is pretty long. It started maybe something like 15 years ago. It's very hard to reconstruct the history. So again, we have a kind of parallel development, and when we met, we realized we have almost the same story, and then we decided to develop it. And I hope in a very soon future we will put a paper on archive. Okay, so just I'll start with the main definition, but I'll start with a story with linear algebra. So it's linear algebra. And now suppose we have vector space of some finite dimension, and I denote by Q C of V the space of all C-valued quadratic forms. And quadratic form on V, or one can say the same as map from symmetric square of V to complex numbers, such that there exist real bases, and form will be diagonal form. Lambda I some non-zero complex numbers. And now I put just one main formula. It's kind of essentially one formula which you have to remember from my talk. Sum of absolute value of arguments is less than pi. So thus, such a form we can call allowable form. In particular, you see none of eigenvalues could be strictly negative. So it means that lambda I belongs to C minus negative numbers, and argument is well defined. And this space of allowable forms is open subspace in space of non-degenerate symmetric matrices. Okay, which is also open dense part in space of all matrices. Okay, I think everything is clear, and the main formula which you should remember during my talk is this inequality. Now, let me tell you something about this domain. Yeah, so I draw this gray blob, and this will be this thing will be GL DC modulo O DC. It's a space of non-degenerate D by D complex symmetric matrices. And here inside you get certain picture which roughly can be drawn like this. I have interior of this gadget. So Euclidean scalar product, kind of positive definite real scalar product, will be some sort of middle dimension and sitting somewhere like a core of this open domain. But then this domain meet each other in things with Lorentzian signature. And signature I will choose as mathematician plus 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 in Euclidean, minus plus 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 Lorentzian, not plus minus 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 plus. It's just like, yeah. So Lorentzian signature is really the boundary, because in Lorentzian signature you get one of kind of lambdas is very close to minus negative real axis, and all the rest are very close to positive. It's a limiting behavior when almost all arguments equal to 0, 1 is equal to pi, but it could be plus pi or minus pi. So you see that you can attach this Lorentzian limit in two ways. So in the small neighborhood of Lorentzian signature, you get two connected components of my domain. And what are kind of general facts about this domain? That I will not give the proof. So first, this thing is contractible. But if consider its closure in GLDC divided by ODC, it's homotopy equivalent to a circle, which is like this, roughly this picture which I draw is homotopy equivalent to a circle. The second property is that this domain is domain of holomorphy. And at the very end of the talk, you'll see it plays a certain role. And also this very nice property, if you have this allowable quadratic form, if you restrict to any subspace, then I get again non-degenerate allowable quadratic form. So it's like for positive definite forms, you can restrict to any subspace to get positive definite. Okay, so that's all basic facts about geometry of this guy. And now maybe I'm ready to give you a definition. What is QFT in our sense, or unitary QFT, in fact?
Maxim, would now be a good time for some questions.
Yeah, maybe there are some questions about this previous space.
So there's a question from Theo Johnson-Fried.
Yeah.
He's pointing out that the boundary also seems to contain other substrata where multiple eigenvalues go to -1.
No, it's impossible. Because some of absolute values of arguments will be multiple of pi. Only one eigenvalues can go to negative.
Makes sense to me, yeah. There's a question from Edward Witten. I don't understand the definition. Did the complex vector space have a given real subspace?
No. No, just a second. And no, I speak not about complex vector space. I have real vector space and complex valued quadratic form. It's a property of this quadratic form. It could, in some real basis, will be diagonal, and this number satisfies this inequality. I hope it's clear.
Okay. There was an older question by Albert Schwartz.
Yeah.
Just a second, it's jumping here. Are you considering only local quantum field theories?
Yeah. No, I don't understand what does it mean local. Yeah, quantum field theory in the spirit of previous 5 theories, more or less. Yeah, like local. Yeah.
And Jan Seubelman is asking for comments on your property 3. Not sure what exactly he has in mind.
Oh, no, if you restrict this quadratic form to real subspace, then satisfies the same inequality. That's
yeah, makes sense.
Oh, that's it. Yeah. I don't know what to say.
Okay, we're caught up with the questions.
Okay, now I go to the definition. What is unitary CFT? It will be tensor. It will be almost like it is definition of topological theory, but I consider category of morphisms which will be symmetrized. I'll say in a moment what is it. So it's tensor functor to category of nuclear Fréchet spaces and nuclear morphisms. Yeah, actually both categories will be non-unital. So what are a category of wordisms? I'll say what are morphisms. First, morphisms are manifold, maybe the boundary, compact manifold with boundary, and boundary will be really important, will be co-oriented. So it means that it's just decomposed in 2 pieces. Yeah, so it's again usual picture. And GC is a complex metric. It's section of the bundle which on point X you consider QC of tangent space. You consider the section of the bundle, and that's essentially the definition. And from this definition, you can see what are objects. If you know what are morphisms, it's clear when 2 things you can compose. Yeah, actually, I will probably be for the stock. I will my manifold will be of C omega, will be real analytic, and this complex metric will be also real analytic. And then objects are completely obvious in this framework. Objects will be d-1 dimensional closed manifolds plus color, a kind of germ of some tubular neighborhood, also co-oriented, and plus a metric on color. and definitely such things you can compose. The tensor structure is given here by disjoint union, and nuclear vector space we make tensor product. Actually, nuclear Fréchet spaces are very simple gadgets. Nuclear Fréchet space is just projective limit of some map of Hilbert space, some inverse diagram of Hilbert spaces. And Hilbert spaces are with countable bases. And all operators should be like Hilbert-Schmidt operators. So infinite matrices, sum of square matrix elements is finite. Yeah, so it's something pretty concrete. And maybe I'll just put some notation. Notation is if I get this variety with color and metric, then the object which associated by this functor denoted by H sigma, which is not Hilbert space, just a nuclear Fréchet space. And if I have manifold with a boundary, then I associate psi m, and psi m is a map from Hilbert space of, let's say, negative part of the boundary, space to positive parts of the boundary. If it will be only output, it will be a vector in some space. It will be like wave function. Okay, so that's the definition, but these things should satisfy some axioms. Will be essentially 3 axioms. One axiom will be holomorphicity. Second axiom will be Simi continuity. And third axiom will be positivity or unitarity. Okay, so my plan is the following. I will discuss what are axioms, what are corollaries of axioms, and then I will explain why this inequality. There are 2 different reasons. Okay, so we'll start with holomorphicity. Okay, so I recall you have spaces associated to the scalars and also wave functions. The first property is that this nuclear spaces form holomorphic bundle on infinite dimensional manifold. This complex matrix satisfies this inequality of a given color or germ of my hypersurface. This is some infinite dimensional complex manifold. And holomorphic bundle, I mean, it's a bundle on finite dimensional families. And for nuclear spaces, it's kind of okay, speak about infinite rank bundles on finite dimensional spaces. And similarly, psi m should be holomorphically dependent on space of complex matrix on this M, my d-dimensional manifold. Yeah, so that's all. I just want to stress it's kind of all this holomorphic. It's for finite dimensional families. Yeah, it's kind of a well-known cheap way to do infinite dimensional manifolds. But also, when we speak about things like manifold or this color, things is defined up to a diffeomorphism. There's also covariance. So it means that both H sigma is on this H sigma acts diffeomorphism, consider again real analytic on the scalar sigma, and psi m is equivalent this action of diffeomorphism of M, real analytic diffeomorphism of M. So what is going on? We have some holomorphic object in the action of some infinite dimensional real group, and we get invariance on the action of real infinite dimensional real group. So let's discuss just one simple example. When manifold is empty, then HDM is C, and then psi M is just what's called partition function. It's a complex number associated to any closed manifold. Yeah, so ignore boundary for the moment. So what we have? We have a GC going to this partition function of M and GC is a holomorphic function on infinite dimensional complex manifold of this complex matrix on M, and invariant under action of infinite dimensional real Lie group, infinite dimensional diffeomorphisms of M. Then I claim that the thing is invariant under action of what to be complexification of this group. What does it mean? So one can proceed in the following way. So we have, suppose we have my manifold with complex matrix, real analytic manifold with complex metric, because it's real analytic. It means that it automatically sits in a germ of a complex manifold, a holomorphic manifold, gets certain inclusion, M to MC. This will be complex d-dimensional manifold. And this will be a holomorphic section of symmetric square of cotangent bundle. MC, kind of a holomorphic analog of a metric. And our metric is pullback, and GC is pullback of GC holomorphic. Yeah, so in real analytic case, one can always complexify this picture. Now we can proceed the following. This following way. So we consider again. Okay, so draw this gray thing will be now. This will be MC. And now inside I have my manifold M. Now I try to consider the following space. I consider space of all map A tilde from M to MC, A tilde close to I. It will be again some embedding, totally real as a totally real submanifolds, and it's infinite dimensional complex guy. Which contains totally real slice, namely you consider arbitrary diffeomorphism close to identity, and then embed to MC. F diff omega M close to identity. Yeah, so what we see, so what we have some infinite dimensional complex manifold of deformation of maps from M to MC, which contains totally real infinite dimensional guy. And on this totally real guy, my function, partition function, is the same, is constant, because I just change the coordinates. So it means that it's constant on this larger space itself. So Z is constant here, hence constant here. And what is the conclusion from this picture? That if you consider simultaneously interaction of the holomorphicity and invariance under diffeomorphism, you say that the following happens. We have this MC, we have here my submanifold I of M, and we move it arbitrary way to some closed submanifold. Again, if it's sufficiently close, it will satisfy this inequality. And if you move, the partition function will be the same. So the partition function really depends only on this complexification. And the choice of real picture is discrete. It's a choice of isotopy of these allowable submanifolds. So this kind of dual picture, instead of allowable metrics, complex metrics, we consider allowable to be open condition, totally real submanifolds. In MC and GC. And if you move it continuously, nothing will change. So the partition function will be the same, and remaining holomorphicity will be holomorphicity on this GC up to holomorphic diffeomorphisms. Yeah, so that's essentially the picture, and maybe right now I'm ready for some questions if there are questions.
Yes, there are a few. So well, some of them have been answered by people in the audience. I'll skip those. But Jan Soberman was asking a while ago, when you described the collar, there's no standard form for the metric on the collar. You allow all metrics?
Well, just any metric on the collar, yeah. Again, satisfying the same inequality pointwise.
Okay. And then there was a question from Arnav. Are you not imposing any higher categorical data? Will you be able to see extended operators?
Definitely not, no.
So will you be able to see extended operators in this framework?
What do you mean? Okay, I don't know.
And
no, I definitely don't want to go to high categories.
Okay.
Okay.
Yeah, there have been other questions, but they were answered by the audience.
Okay.
So let's skip those.
Good. Yeah.
Oh, here's another one from Nikita Nekrasov. Are there many more complex metrics than there are real submanifolds?
No, if consider real analytic, I think it's just the same language. You have complex manifold and total real submanifold satisfying this inequality, or real analytic metric satisfying this inequality. Just equivalent story.
Here's one from Claude Lebrun.
Yeah.
Do the deformations that do not move the boundary have a special status?
Not really, yeah. Boundaries also can move freely in a sense. Yeah, but as a holomorphic hypersurface. And totally, the boundary will be replaced by holomorphic hypersurface, and you just move freely a totally real hypersurface in this holomorphic guy.
And Sharihar Sikander asks, can this be thought, can this be thought of in terms of geometric quantization? And can you say something about the example where M is SUN, modular of all flat connections on the surface?
No. I don't want to relate to.
Okay.
No, I'm speaking very, very general stuff here. Kind of really axiomatics. Okay, maybe I continue.
Yes.
Yeah. Yeah. So the second question is semi-continuity. It's something which is Graeme kind of came to really independently. It was the same story. And for the semi-continuity, one can forget about this holomorphic equations. It's already interesting in pure Euclidean setup. this holomorphicity doesn't really add anything new. Yeah, suppose I get some hypersurface, co-oriented hypersurface. Locally, I can introduce some kind of time. I get family, one parameter family of hypersurfaces, and which I can maybe I can draw some picture. So if my hypersurface is like this, I can approach both from the left and from the right by co-oriented hypersurfaces sigma t. Yeah, I can approach both from the left and the right. And then we get automatically the following kind of sandwich situation. Space associated to the surface maps to projective limit of h sigma t with t is positive, and to it is a mapping from inductive limit from ht for t is negative. And what is the axiom? Actually, the axiom that this is isomorphism. So this h sigma is semi-continuous in this direction, which is kind of reasonable for nuclear Fréchet spaces which are projective limits. So one projective limit is equal to another projective limit. But what is this subspace which sits on the left? This space I will just denote by h sigma small. It will be certain subspace, a dense subspace eventually of this h sigma. And kind of interesting fact which just follows from nothing, that h sigma is h small sigma star star. Yeah, stars mean two different things here. Here star, it means it's dual, continuous dual, and here star, it means it's opposite co-orientation. Yeah, in fact, it's really perfect duality. It's not only these things, but also h sigma dual is equal to h small. Yeah, so it's really perfect duality. So one space is dual to another. And the argument is the following one. So h sigma is obtained as a projective limit by our axioms is equal to projective limit. And maybe I can just put sigma 1 over n. This t will be 1 over integer. But now I consider this picture, co-orienting them in kind of funny way. I co-orient in this way, and if you see what are maps here, you get a sequence of maps from h. You get map from to h sigma 1. This is a map from this to this guy from h sigma 1/2 dual. This is a map to h sigma 1/3. This is a map from h sigma 1/4 dual, and so on. So you can form this infinite sequence of maps between spaces and dual spaces. And if you consider only each odd element, you get cofinal sequence, you get the same limit. But now consider this intermediate dual guys, who also gets a cofinal sequence, you get the same limit. So you see that it's equal to inverse limit of this h sigma 1 to n dual, and then applying duality, you get one of the statements. Okay, yeah, so it's really very cheap argument based on the kind of infinite division of for any real number. This is a small real number, nothing else. But that says that this structure is extremely rigid. One cannot make any mistake with the spaces. If one make kind of mistake in functional analysis, your spaces will be too large, then dual spaces will be too small. But then you have kind of contradiction because those inductive limits are made from the same nature. Okay, so that's all story which we can want to say about Simi continuity, and it served to repair the problem that my categories were not unital categories. It's because it's really about approaching identity element. Okay, so that's very general remark. And now the third story is about positivity. Yeah, in fact, first I should maybe say about reality condition. A reality condition is the following. If you consider manifold, and make complex conjugate of my complex metric and also change orientation on M. Actually, I was a bit sloppy. I told you about this story was on manifolds, but manifolds should be presumably oriented, maybe spin, which has nothing to do with co-orientation of hypersurfaces. So if you consider, if you change this, make to complex conjugate metric, let's go to change orientation, then it will be ZM GC bar, and similar for and same for sigma. So the Hilbert space associated to sigma and metric and bar and opposite orientation of color. And I take bar is equal, whatever is equal to H sigma G sigma bar. Yeah, so I get a real structure on my category and on the functor. And the axiom, which I want to say, what is the axiom? That assume that my color assume we have isomorphism, or maybe of complexification. I don't care. Then I get identification between space with complex conjugate and kind of dual. And for dual, if one analyze what really goes on, if one gets such a situation, then one get a map between the small part sigma to this complex conjugate. Then I get a pre-Hermitian product, kind of maybe pseudo-Hermitian product. And axiom, it is positive definite. One can analyze what does it mean if you go to complexification. Then you have this isomorphism between complex conjugate and opposite orientation, and this thing is opposite co-orientation. And it's very simple geometry. I don't want to bother you. It's actually equivalent to some classification of space-like hypersurfaces in Lorentzian signature. Yeah, so what is going on? If you get space-like hypersurface, you choose some kind of normal coordinate. If you get this space-like hypersurface in Lorentzian signature, one can use kind of orthogonal flow and geodesic flow in orthogonal direction, and then multiply by IT, get complex valued metric, and which will be satisfy this property and will satisfy this condition. Yeah, so that's all my axiomatics, and now I'm ready for questions if there are questions.
So let's see, there were a couple of questions from Greg Moore. One
Yeah.
was, you're careful to say that the codomain is a Fresnel-like space.
Yeah.
You want to know why do you need those conditions and how important
Fresnel nuclear space. Because in this Simi continuity, I think nothing else can appear. If you consider direct kind of projective limits of very contracted operators, whatever functionalness you put in, you end all of these Fresnel nuclear spaces. And Fresnel nuclear space is also very nice because tensor product is canonical, and yeah, that's it.
He's also asking about the definition of H small in particular. Is it compatible?
H small is yes. H small is it's a formal inductive limit from this picture. I don't know what is it. Yeah, one can make the following analogy in maybe if one can make the following just a second.
So is it compatible with time reversal in particular?
No, H small has different meaning. Yeah, maybe I can say the following. Suppose you have some open disk in C, yeah? Disk of radius 1. And see the holomorphic function. Then it's a projective limit of holomorphic functions on disk of smaller radius, where r is less than 1. You can restrict to smaller, I think. And if you consider this on smaller radius, so you can make L2 norms. It will be even some Hilbert spaces. So it will be always projective limit of Hilbert space. But now consider functions which are holomorphic a little bit on a larger thing. Will be converged on disk of radius strictly bigger than 1, but we don't specify. It will be inductive limit. It will be like over convergent series. Yeah, that's a rough picture of what is going on with this functional analysis.
Those are all the questions we have so far.
Okay. Now I should draw some conclusions from axioms. Yeah, one can prove the following thing. It's a bit long story. If you get global hyperbolic space, space-time, and so you get kind of sigma minus, sigma plus, and sigma minus, sigma plus I assume compact, so it's, don't really go to infinite space limit. Then there exists a unitary bijection between these guys, like in Friedenhagen axiom. You get unitary operator. In fact, this proof reduces essentially to dimension 1, because this global hyperbolic space-time, it means that you get kind of like flow, you get time. And in dimension 1, it's some kind of funny argument, which is in a sense new in quantum mechanics, how to prove that operators are unitary. So consider my complex manifold will be C, and the metric will be dz squared. I get this locally, any holomorphic metric looks like this. And then if consider allowable manifolds, which will be, it will be kind of oriented paths which always go to the right. So real part will be a coordinate on this submanifold. And then if you consider evolution operator, how to define this evolution operator? Because you go to H, you define to the smaller subspaces, essentially approximate by some pictures like this. Yeah, evolution operator should be associated to kind of limiting since you go in direction IR. But if you approximate by things like this, then you go to Hermitian conjugate, goes like this, and then you can contract the things to nothing. Yeah, that's a pictorial proof, but it can be made a rigorous proof. And to make that you get unitary operators, then similar get subalgebras are associated to domains in this global hyperboreal space. So it fits with this Friedenhagen and axioms, but also it speaks with kind of local observables in pretty obvious manner. If you have a point, then you can consider coordinated outwards disks, spheres, and define HP of point as a projective limit of H of the things with radius goes to 0. And then automatically, if you get some collection of points here manifold, xi, and you get element phi of xi which belongs to these spaces, then you can make correlators. Yeah, so it's, one can make some relation to all other axiomatics. Yeah, so it's all pretty. That's how it's really talks with all various axiomatics. This new formulation, and maybe I just want to add one more thing. Even in Euclidean setting, kind of ATIA types axioms implies something really dramatic, which is some object which mathematicians, in a sense, cannot invent if they don't know what is field theory. You can consider partition function of flat torus. So you get function, if you consider flat torus, shapes of flat torus, you get some double coset, SLDZ, you get some complex valued function on this space. And it has the following property. You can parameterize d-dimensional lattice, can parameterize by some d-1 dimensional lattice in Rd-1, and then you add kind of extra generator by moving in particular direction by some Euclidean time t and making by shift x, x belongs to Rd-1 modulo this Zd-1, and t is positive. Yeah, and the property is the following: if you fix this lattice, but t and the shift will be free parameters, and partition function, which depends on x and t, and this lattice will be sum over some basis on Hilbert space associated to d minus dimensional man torus. Will be certain eigenvalues of energy times 2 pi square root of -1 some momenta x and maybe some mu alpha. Mu alpha are in lattice and E alpha are complex numbers, and real part of E alpha goes to plus infinity. Yeah, so it's some remarkable class of functions is double cassette space, and I think it's horribly overdetermined system. One cannot, without field theory, in a sense, to find any solution of this thing. And this axiomatic leads to some kind of analytic bootstrap, which is easy to prove in dimension 2, that this Z extends to quotient of this domain divided by SL to DZ. So you get kind of really nice holomorphic object with the same properties, still very overdetermined. Okay, now I go to the kind of final part of my lecture. Why this condition? Yeah, up to now it was completely black box. Yeah. I want to give kind of two informal arguments why it's necessary. Oh, sorry, and why it's sufficient. So this condition, actually it was observation of Graeme, can be formulated in the following way. For any p between 0 and d, or maybe d minus 1, doesn't really matter, and for any real p form alpha, not equal to 0, the real part of the integral of alpha wedge cross wedge alpha is positive. It's essentially, it's kind of pointwise condition. It's exactly equivalent to this Graeme. So what does mean alpha wedge star alpha? If you had general Riemannian manifold, then you know what this is, but now it's some expression in metric and you make analytic continuation in metric. Why it's necessary? So the idea is this, what we can study, we can study something called higher gauge theories, actually abelian gauge theories. It's well-known problem. The space of fields roughly is the following. You integrate over what? Consider of p forms which are closed and cohomology class belongs to HPMZ. It's a very rough description. You get the 6 integrate exponent minus integral of this guy. Maybe multiply by some coupling constant. Yeah, it's in Euclidean setup. It's completely perfect theory, and it's should extend to all this world. And if you consider Z of torus is constant complex metric, you get the following concept. It will be determinant of Laplacian to some complicated power multiplied by determinant of this metric G to some another complicated power. And then you get certain theta function. You take sum over all alpha with constant coefficients and automatically close and homology class are integer. So they're really labeled by homology class. And you get exponent of minus c integral of alpha wedge star alpha. And you see that this guy, if its real part is not positive, will definitely be badly divergent, and the story will make no sense at all. But if it's convergent, then all things is everywhere defined, and here we get a perfect story. This high gauge theory, it's something very simple. If p is equal to 1, it's maps sigma model to maps to a circle. If p equal to it, you get usual U1 gauge theory, and something similar goes for high p. And now the next thing is why it is sufficient. It's more fishy argument, but it's reduced on most classical white axiomatics and this weak rotation Servaler-Schrader axiomatics. Story is the story is the following. The classical way to go to white maximum to Euclidean axioms is the following observation. There is certain thing is called extended tube domain. Which is the following guy. It's a set of collection of n points in CD in complex space, and xi is not equal to xj, and such that there exists a rotation and right SOD minus 1, 1c. It's the same SODD, but I refer to special basis, and there exists a permutation such that imaginary part of gx sigma plus y minus gx sigma I belongs to light cone, positive light cone. If you get so you get some open domain in configuration space, so you get this big domain dn. Dn is open domain in conv n of the CD. It's open domain, and all these correlation functions are analytically extended to this domain by Weidmann axioms, and they contain configuration space of Euclidean domain. And now Dn contains conv Rd Euclidean. That implies that you get symmetric function of them. Now, what is the observation? Let's try to think what possible total real subspace we can consider in CD, which are not Euclidean, and such that still for any configuration space, this correlation vacuum expression value will be well defined. And the claim is the following: let V in CD will be totally real affine d-dimensional subspace such that quadratic form is allowable. Then for any n, configuration space of n points in V sits in this extended tube domain, and hence we have correlators on this domain. How to prove it? You prove it, the proof is used on some kind of Bochner type argument. If you have this vector space, you project to Euclidean, Rd Euclidean, and it follows from all properties its projection is 1-to-1. So it V is obtained from Euclidean by some kind of tilting, and you go to transformation xi goes to xi times square root of lambda I, and then Rd goes to V. Also get many variables. So in particular, for example, here is this, you get action of certain Simi group. You can see the xi goes to xi times exponent of alpha I. And if imaginary part of alpha I are the following, it's between 0, 0, 0, and then something theta for some I, and theta between pi over 2 minus pi over 2. Then one can see that it sits in our domain, and we get holomorphicity. But there's no condition, no constraints on real part of alpha, and one gets something like tube domain. So imaginary part of alpha belongs to some kind of union of this pieces of coordinate planes. It's not open domain, but there is an extension of Bochner's theorem. Actually, I was surprised it wasn't classical. That any function holomorphic in appropriate sense is pull back in this subset of C to power D, such that imaginary part lies in this strange body, then automatically extends to the convex hull. And convex hull gives exactly this inequality, sum of arguments lambda alpha is less than pi. Okay, maybe I'll stop now.
Well, thank you very much. We've had a lot of questions in the last 15 minutes, and I didn't want to interrupt you, so I think we'll just let people raise their hand, and then they can ask you in person.
Yeah, okay, it's the best. Yeah.
So I do not see any raised hands now. Am I missing? Am I looking in the wrong place?
Don, I think Edward's hand is raised.
Sorry? I don't hear you well.
There are a few raised hands.
Okay.
Are you able to call on them? I don't see them on my screen.
Okay, yeah, because I have then to stop share, then I probably can see the raised hands. What?
Maybe.
I see. Oh, I see some raised hands. Just a second. I see some screen. But when I type, it doesn't. Yeah. I can't really open the menu.
Okay. So let's take a question from Edward Witten.
Okay.
I didn't.
I don't hear you. I don't hear you.
Edward,
I don't have a question.
You don't have, okay.
oh, sorry.
I think Marco Gualtieri has a hand raised.
Marco, can you unmute yourself? Well, my screen says that Greg Moore has a question. Let's try that.
Yeah, maybe if I stop share, I can really read questions.
Yeah.
Let me try it.
Greg, are you able to ask?
Greg may not still be on.
He seems to be on.
Oops.
He says he can't unmute.
Hello.
Oh no, I see.
Hello. Hello.
Oh, I see some
Hello?
questions. Yeah.
Can you hear me?
Yes.
Yeah.
Now. Okay. Good. Yeah, I had a couple of questions. Could you go back to that the higher abelian gauge theories?
Then I have to share my screen. Okay. Then.
Well, no, we don't need to share the screen. So you summed over cohomology class.
Yeah.
Of e to the minus the integral.
Yeah, this expression. Yeah.
Well, don't you need to choose a distinguished representative in the cohomology class to make?
Yeah, but I am in a flat torus. I can see the form with constant coefficient. This will be representative.
Okay, this would be a problem with other metrics, right? Because you'd need to choose something like a harmonic form, but you're using complex.
No. I wrote an answer for for flat.
Yeah, but this,
I wrote an answer for flat.
This kind of formula is
torus.
also true for general metrics. This kind of formula is also true.
Yes, of course, definitely it's true. And I claim that it will be still okay.
Okay, I have a harder question.
Yeah.
So can you formulate, well, let me preface it. So physicists like to say that the tangent space to the space of conformal field theories is the space of exactly marginal operators.
Yes.
It'd be nice to prove that in an axiomatic system.
Yes, actually, it was a really disaster with axiomatic of conformal field theory. This was the first question for which there's no good proof. Yeah.
So well, my question is, you have a new set of axiomatics. Does it help?
No, I don't think it will help. In case of conformal field theory, it really doesn't really add anything new into dimensions.
Okay, is there a formulation of the renormalization group in your
maybe.
view of?
So I did. Yeah, should be. I didn't thought about it, but it should be.
Let's take the next question from Marco Gualtieri.
Yeah.
Hi, I had two questions, but Edward answered one of them in the chat. This is very useful. So the second question is, in the picture where you were looking at a real submanifold moving in the complexification and taking the induced metric, what does does the inequality have a special geometric interpretation in that?
No,
frame?
no, no. It's completely formal game. Yeah, one can before explanation one can replace by anything. Yeah, this by any open domain. Yeah.
I just wanted to make one comment, which is that there's a famous paper of Donaldson from 2000, where he interprets a Kähler manifold, a Kähler metric, as a Lagrangian submanifold in a complexified space. And that as that thing moves, the Kähler metric changes.
Yeah.
I don't know if it's related to this.
Maybe, I don't know. Yeah, I have no idea.
I think that's my question. That was my question, actually.
Ah,
That the sum
Nikita,
of, yeah, I think that this condition that the sum of the absolute value of arguments less than pi has some relation to the slope condition for the special Lagrangian. Special Lagrangians.
It's absolute value. It's not. Yeah.
It's not.
Yeah, it's really bizarre. Yeah, I don't know.
I see. Okay. Yeah. Or maybe for some. So if instead of taking absolute values, you will take plus minus.
Yes, yeah, because
choice of plus minus
will be lambdas in upper half plane and lower half plane, and you get.
So you have 2 to the n chambers, maybe.
Maybe, yeah.
So that will partition your domain into the chambers.
Yes, of course. Yeah, no, definitely, because it's not 2 to the n because you don't order them. Yeah, just maybe. And how many eigenvalues in upper half plane?
Okay.
Yeah.
Okay, let's take a question from Slava Richkov.
Yeah.
Hi, Maxim.
Yeah.
So my question is about not so much about your axioms, but about the perspective that they may give on some unsolved problems in Weidmann axioms. So there is this famous unsolved problem that the envelope of holomorphicity of the general Weidmann endpoint function is not really very well understood, except for 3-point function case maybe. So I was wondering if you're
I have actually the last slide which I stopped because I was a little bit over time. Okay. Maybe I can sell in words without writing anything. So my guess for this envelope, for this holomorphicity envelope for this extended tube domain is the following: you consider all possible submanifolds in Cn. Total submanifolds which are allowable and which projects one-to-one to Euclidean RD. It doesn't matter which one you choose, it will be always graph of map RD to imaginary part. And then it gets this complicated idiotic inequality on this tangent map. So the sum of absolute values of arguments less than pi, and consider configuration spaces all these gadgets. And my guess it will be the right domain, but unfortunately, actually we hoped with Graeme that this condition will be convex, and turns out it's not convex condition, so we don't really get good reasons to believe that it's the final answer, but at least it's some pure geometric question which is interesting to study. And also in conformal field theory, it gives some kind of larger domain for correlation function, for 4-point function, for whatever. One can look for this as well.
Okay, interesting. Thank you.
The last raised hand I see is from Nito Kichlu.
Yeah. Hi, Maxim. Can you hear me?
Yeah.
So this question may not make sense from a physics perspective, but I was wondering if it makes sense to stabilize in dimension this condition, your construction. So just by adding a complex plane to your manifolds and then adding the complex metric z squared on it and stabilizing in dimension, is that a viable object to study?
Yeah, but no, it means that you just add extra coordinates on which your metric will be still real. Yeah.
So is there something interesting that happens in the stable limit? Is there any
yeah, and of course one can ask like eventually infinite dimensional example, which will be essentially Euclidean all except finitely many dimension.
So is that
some or maybe infinite
sum your Hilbert space?
Infinite sums will be less than pi. Yeah, of course this condition makes sense in infinite dimension as well. Yeah.
So does it pick out something about your field theory, some functor,
but it means consider field series in high dimensions, and the field series are more and more rare in high dimensions. Okay.
So we have one more hand from Jan Zwiebelman.
Okay.
Yeah, I somehow missed whether you answered the question about the moduli space of deformations.
No, the answer is it doesn't help. Yes, it's axiomatics.
No, not for CFTs, but just you do have some moduli space of quantum field theories which satisfy your three axioms.
Yeah. Yeah, but no, for example, this equation, even this partition function of flat tori, does it really locally finite dimensional or not? I have really no idea.
I remember that long ago, I mean, when we played with Weightman axioms and we kind of studied moduli space or whatever for quantum field theories on metric spaces. It's kind of a very wild.
Yes,
and there was some conjecture for that. So, but this is much more precise.
Yeah.
So
Yeah, I don't know. Yeah. In fact, also I want to say that in about 2 weeks, but it will be pretty early for most of you. It will be really Eastern Hemisphere seminar. It's 3 p.m. in my time. I will give talk on another analyticity, but like for resurgence and which is not related to this story at the moment. Yeah.
Joey, do you want to ask a question?
Yes, thank you.
Okay.
Is this to understand the partition function for the flat torus better?
Yeah.
So this was a product of the determinant of the Laplacian, one other determinant, and sum over some cohomology classes of a function.
Yes, yeah.
So this function depended on C, the coupling constant.
Yes, on positive coupling constant, yeah.
Is there some, I mean, can one think of this in terms of, say, L functions, which are generally defined in the right side of the plane, and there's a functional equation which extends them to the full complex plane?
I don't know.
Somehow...
No, this object, partition function of flat tori are actually very interesting, guys. They live on the same space which number series, like this double coset space.
Right.
But for many years I thought, how can I relate kind of mass forms or homomorphic forms to these guys? And this little problem, mass forms has expansions which are Bessel functions, very close to exponents, but not exactly exponents. And should be some interesting integral transform going from one to another.
Right. I see. Okay. And the determinant of the Laplacian was the regularized determinant.
Yes, yeah.
Okay.
Samson?
Hi. I was trying to ask a question about anomalies. During the talk, I was writing some messages, but I don't.
Yeah, I'll read it later. Yeah.
So you require diffeomorphism invariant.
Yes.
But we know that there are theories in 4K plus 2 dimensions that don't have diffeomorphism invariant.
Okay. No. My axiomatics for series. No, it was really based on diffeomorphism invariance. All logic was based on.
Right, I understand, but so it does not include the gravitational anomalies when there.
Yes. Or if consider some kind of like anisotropic series, partially complex, partially real, it's a different game.
Thanks.
And I think we've asked all the questions. So let's everybody thank Maxim for the fascinating talk. And we'll meet again, I believe, next week.
Okay.
Thank you.
Are you going to switch it off or leave it on for a while? Because I want
Would you
to
like
read
me to leave it on? You can stay on, sure.
No, because I want to read questions. I'm afraid it will disappear.
Oh, well, I think
I can send you the. I can send you the chat list.
Oh, you can send me the chat, and I'll try to see it because I had no time to read it. Okay.
Okay. So again, thank you very much.
Okay. Thank you.
Bye-bye.
Bye.
Thank you, Maxim.